Have you ever wondered how this film camera could turn into this digital camera? Let me take you back into time to when sensors were first developed.
In the early 19th century, cameras relied on film, a chemical process that captured light onto physical material. And then we had CCDs introducing us to digital photography. But today, you can find CMOS sensors in almost all devices capable of photography.
But actually, there's so much more room for improvement. I guess you've heard of nanoparticles before. What if I told you that nanotechnology could be implemented into building these sensors? Let us introduce to you the revolutionary invention of carbon quantum dots.
Now, what are carbon quantum dots? Quantum dots, QDs, specifically are nanometer-sized semiconductor particles that have unique optical and electronic properties due to quantum confinement effects. The emerging application of QD-based sensors are responsible for capturing and converting light into electronic signals that ultimately form images. Now, let's take a step further. Carbon quantum dots, or CQDs, are a new class of quantum dots, efficient, cost-effective, low in toxicity, and much more customizable. Remember the quantum confinement effect? This is the key principle behind the unique properties of CQDs, allowing for tuning of their electronic and optical behavior by simply controlling their size.
Let's get into the working principle. In nanoscale materials like CQDs, the small size of the particle restricts the motions of the electrons, confining them within the boundaries of the dot, forcing them into discrete quantized energy levels. Smaller CQDs have a larger band gap and emit higher energy light, vice versa. This is the carbon confinement effect that enables control over their emission and absorption of light. Despite their potential, the widespread adoption of quantum dot-based sensors is hindered by various challenges. Hence, let's delve into the viability and overall process of how CQDs can be implemented into imaging today. The most optimal step we can take is by enhancing the synthesis of CQDs. Therefore, we propose hydrothermal synthesis aided by microwave irradiation technique. Usually, a Teflon-lined autoclave is used in hydrothermal synthesis, but in this process, the carbon precursor and water solvent are placed in a microwave reactor instead, where rapid and uniform heating occurs. The carbon atoms then undergo carbonization, breaking down into smaller particles and eventually forming CQDs. The simple setup of hydrothermal synthesis allows larger scales at lower costs, combined with the microwaving techniques that significantly reduces synthesis time, energy consumption, while improving the yield and quality of CQDs, make a total game changer. Thus, better control over particle size and surface properties are also achieved. Additionally, substituting to green precursors such as plant extracts, agricultural waste, and biopolymers increases sustainability ultimately. And what do you know? We've succeeded!
Now, I'm going to tell you why you should care about CQDs. First off, they enhance photoluminescence, or in other terms, low light performance.
CQDs have excellent light absorption and emission properties, which can improve image quality, capture brighter and clearer images with higher sensitivity.
And next up, tunable properties, or in other words, the flexibility of the sensor in other fields.
The optical properties of CQDs can easily be tuned by changing their size, surface chemistry, or sensitivities method. This flexibility allows them to be adapted to various imaging application fields.
And finally, environmental friendliness.
Unlike some traditional quantum dots, which can be toxic due to the presence of heavy metals, CQDs are non-toxic and environmentally friendly, making them safer for widespread use in consumer products.
Now let's talk about viability. To fully leverage the advantages of CQDs, we need to overcome two main issues. The first being signal drift. To combat signal drift, we can implement two techniques. The first being encapsulation and the second being surface passivation using protective coatings. These can prevent oxidation and degradation of the sensors, maintaining its performance over time. Next, we need to reduce how non-target analytes bind with the functional groups in CQDs. To do that, we need to functionalize CQDs with these specific recognition elements to improve selectivity.
To conclude, we believe that other sectors can also benefit from this research. The promising potential of CQDs to achieve Sustainable Development Goals number 9 and number 12 should not be overlooked. That's all from us. Thank you. Bye!